We're back.
We are back, and this is Module 2 of Unit 2.
Of AS Physics.
Oh yes. Behind us are some circuit components.
You have to know them all, unfortunately.
You do. In the exam, might ask you to draw out a circuit, and it'll tell you what the parts are, but it won't show you what they look like.
So you've got to know how to draw them. Vice versa, it could draw them and then ask you what it is.
Yeah, so we're going to go through them all right now.
Yep, there's a pen. I'll take red.
You'll take red?
I like red.
I
like blue, but I'll use red. You can go first.
Alright, so right at the top we have a junction.
Of conductors.
Of conductors, but I'm just going to write junction because that's what it is.
Next we have overlapping conductors. They do not intersect.
No, they're just sort of wires on top of each other. You can move them. That'll be fine. Then an open switch, and I'm going to call it an open switch.
Brilliant. 10 out of 10. Next we have, and don't get tripped up, this is the cell.
Yeah, batteries are made up of cells, and that's what that is the battery.
Just on its own is a cell. Some people might put battery or power source, it's not.
Yep.
Next we have a terminal.
It is a terminal. That was a plane. Thanks. This is a lamp.
A lamp. Some form of a light source.
Yep.
Just a rectangle on its own with the wires is a resistor.
The next one is a variable resistor. It's got an arrow in it, so it can be changed. Alright, the resistor.
Next we have a potential divider. I'll wait until it's finished. But potential divider, and then we'll swap.
Yep. Potential dividers split up the circuit and split the voltage. Right, top of this one, that is a fuse.
Next one, you can sort of tell by the way it looks, it kind of looks like one. A heater.
Yep. These ones we're more familiar with is an ammeter.
Then a voltmeter.
Then something you might be familiar with is a thermistor. It's a resistor dependent on temperature.
Yep. As temperature changes, the resistance of this thing will change. For the top end students at physics, you might remember from triple science, this is a diode.
Yep.
You don't approach that in double science, but it's a diode.
Then there's a light emitting diode, or LED.
Yep. And finally we have a light dependent resistor.
Like the thermistor, this will change resistance when different lights are on it. And those are components.
Those are components.
Yeah. Well observed. That's what physics is all about.
So next we have stuff, this is all about resistance, this whole chapter.
This chapter is about resistance and resistivity and how that affects circuits.
First we have electromotive force, which is something new.
Yeah, noted as EMF, and that's the driving force in a circuit.
Yes, but if you just first let's picture that your kettle might take 300,000 joules in order to work, and it might take that over 120 seconds to boil the water. If your main supply supplies this 300,000 joules over the 120 seconds, it gives 2,500 joules per second, which is 2,500 watts.
Because watts is joules per second.
It is.
But what sort of tea would the kettle make?
It could make velocity,
insanity,
monstrosity,
faculty,
Mr. T,
capacity,
cavity,
RESPECT.
but probably just PG.
Probably just PG tips, I'll tell you.
Alright. So next we have electric current.
We do.
Which is what this is.
Yeah, let's swap sides.
Although it's still in red. Electric current.
It is something a bit confusing about this.
It says current, but it's measured in volts.
It is measured in volts, but that's because you work it out by using the definition of a volt.
Yes, so it's the formula for working out EMF or electric current is energy transferred
over charge,
which will give it the units of joules per coulomb, which is what a volt is.
Yeah.
Over charge. Which is something new.
It is something new, which we'll be messing around with that quite a lot.
Yep. So next, let's go on to, what's next in the book? Oh look. Practical uses.
Alright, go to practical uses. Yep. We're back.
With the uses of EMFs.
Okay, well, batteries.
Yeah, you use them all the time and they actually use EMFs.
They do. So if we have a clock running from a battery of 1.5 volts,
every coulomb of charge that leaves that battery will have 1.5 joules of energy. That's what that means.
Yeah. Equally, if we scale up 6 volt battery, so
Yep.
4
We'd have
1.5s.
4 1.5 cells. That's why we remember the components. We had cell and then battery. You'd have 4 cells in the battery, each with 1.5, adding up to 6. Every coulomb of charge will have 6 joules.
Okay, that's pretty much that.
Question now.
Question time. We've got a question from page 95.
95. Yep. It's question 2 we're doing here.
Yep.
You ready to write it up?
I am ready to write it up. So 2A is
2A says how much energy is transformed from chemical to electrical form when 1 coulomb of charge passes through the cell in question 1 above, and question 1 above is a 1.5 volt cell.
We should mention that all batteries, the energy stored in them is actually chemical. You need to remember that. It goes from chemical to electrical.
Yes.
Thought I'd mention it.
Yeah, it should.
So, as Wayne just said before,
If we've got a 1.5 volt cell, every 1 coulomb will have 1.5 joules, and it is that simple. So it's 1 coulomb, 1.5. The electrical transfer is 1.5 joules.
done. So, part B.
Part B, going a little bit harder with each question. How much charge passes through the cell in 1 minute when it is delivering a current of 0.5 amps?
Brings it back to our old equation,
Q
Q equals IT. So, we have 1 minute, which is 60 seconds,
Remember, it's got to be in seconds, not minutes, because it's a standard international unit, is seconds.
0.5 amps.
So you're going to have 60 times 0.5,
30.
current times time is 30 coulombs. And that is quite simply your answer for charge.
It is. So, then we have C.
Part C, yep.
Put it here.
How much energy is transformed by the cell in 1 minute?
Well,
Here we have 1 coulomb in a 1.5 volt cell gives 1.5 joules.
scale it up to our 30 coulombs,
It's that times that is essentially what we're doing.
which means it's 45 joules.
30 times 1.5.
Okay, part D.
The power of the cell is the energy that is transformed per second. What is the power of the cell?
Okay, well, the equation for power is joules over time,
We have this many joules in this many seconds.
so 45.
5 over 60 is 0.75
It is, and that's how many watts?
joules per second. What?
Okay, is there a part E as well?
There is a part
Oh my
E.
goodness, this question goes on forever.
It's split into 2 parts, but not a part 1 and a part 2. It's just one big question.
Alright.
So first, is the power of the cell the same as in part D when it is delivering 0.25 amps?
Okay, so if we look back at, do you want to get a blue pen?
We'll get a blue pen.
If we look back at the amount of amps we had before and our equation of Q equals IT, if we're basically saying what happens if we decrease I to the amount of joules or
Yes.
watts. So if we halve this, that's the same as halving that, which is then the same as decreasing that.
That's then times by that to give you this answer. This will be half, so that times that will be a much smaller answer.
So I'll go
Smaller over the same is going to be
less.
less.
So it'll decrease it.
And it's quite that simple, so it's a no. It is not the same as in part D.
Because
You don't have to prove it, it's just asking for a yes or no, but that is how you go
That's
about
how you get that.
logicking it.
And
The next part of the cell,
oh goodness.
how is the power of the cell, the total time taken, and the chemical energy stored in the cell related?
It's a nicely worded question. It sounds really evil, but we have to think back to our power equation we went over a few seconds ago.
Yep.
Should know from GCSE this one, where power equals joules in a second. You want joules, you bring over S.
It's going to be power times time. If you can't do that, you can look at the question and have a look at what you've just been doing, because that's sort of what it relates to, but you should know that equation, power equals energy transferred over time, rearranging, you want that to be the subject, because that's what it's asking us about. Power times time equals joules.
And that's the answer.
And that is that. What are we on to next in the book? Let's flip over the
I can't
page.
remember. It is
Potential difference. Let's go.
Alright.
I'm going to evolve.
Potential.
Difference.
What we're now on to. So, Wayne, what is potential difference?
Potential difference is the conversion of electrical energy into some other form of energy, like light or heat, in stuff like radiators and light bulbs.
Sort of the opposite of electromotive
Force,
force, which is like chemical energy straight to electrical.
And that's the difference between them. But how do we measure potential difference, Triv?
Well, Wayne, we have a voltmeter, which we discussed before, which measures in volts, and we have a component, and it measures the difference in volts either side of the component.
Like that.
Like that.
I'm not going to draw the rest of the circuit, that's what that does.
Yeah.
And it doesn't have to be a lamp, could be a resistor,
Could be a resistor,
something like
could
that.
be a diode.
Could be anything, in terms of our components we learned at the beginning. That's what it does, very
Yeah.
high voltmeter,
That's what it does.
volts.
And there's quite a few ways to work out potential difference.
There is.
The book goes
derives them.
Yeah, it derives them all, but I don't think that's helpful to remember them. So we're just going to state them.
We're just going to state them.
So the first one's potential difference, which
Let's
equals...
go to PD for potential difference.
That's a good plan. Energy over charge.
Energy. Overcharge.
The next one says power times time over current times time.
The times can cancel from that.
So it just becomes power
Over current.
over current. Yeah.
And those are the equations. Like I said, we're not going to derive them, so let's just go ahead and go on to a question.
Alright, let's do it. Yeah.
Right.
Okay.
I'll read it out to you.
Have you got the black pen?
Yes, I do. I always do this.
You always have the black pen. Alright.
Alright.
Okay, I'm ready.
We are doing question 3, and it's A, part 1. Okay. An electrical circuit in a small torch consists of a battery of EMF 3 volts.
Right. So you have something that's 3 volts. Oh, it's a V. So I'm going to draw a circuit for this, is that a good idea?
Yeah, that's a good idea.
Alright.
It's quite nice to draw out a circuit, which is where you need to know your symbols just for yourself as well as for the exam. So that's right, we've got a bulb there. We're going to have an ammeter to measure the current, and we'll probably have a voltmeter in parallel to the bulb to measure that. So the EMF is 3 volts, that's labelled up there. The potential difference across the bulb is 2.7 volts when the current is 0.3 amps. So part 1 says calculate how much energy is converted in 1 minute, which is 60 seconds, from chemical form to electrical form.
So you want energy made in a minute.
Yes.
So we
That's
should use
60 seconds.
It is 60 seconds. Step before, the national unit is seconds. You need to keep it all in that, otherwise we get very strange results.
Yes.
So we need to use our original equation, I think.
Yes, first we need to work out charge, which is current times time.
It is.
Current is 0.3 amps, time is 60, so that gives 18 coulombs. And this is now like the questions we did a minute ago, the 18 coulombs in a 3 volt battery, you do 18 times 3,
Which is 54.
54. And that gives you 54 joules.
Alright, so we're part 2.
There's a part 2.
Alright.
Now it's kind of the opposite, introducing the potential difference. It says calculate how much energy is converted in 1 minute from electrical form to thermal energy and light in the light bulb.
Okay, so we're using the light bulb over there, so that's 2.7 instead of 3. Apart
Yep.
from that, it's the same.
It's exactly the same. You do 18 coulombs, which we've already worked out, times the 2.7. I'll give you that answer. 18 times 2.7 equals... You messed up your 18 a bit, didn't you?
It depends on that, I think, a little bit, yeah.
Okay, 48.6 joules. And there is a B, a final part of this question, I'll read it. B says, suggest why the two values in A above are different.
Right. Well, there's only one reason why values should be different, and that's because energy is lost.
Yes.
The only question is where.
Well, the energy that's lost here isn't really lost, it's just converted into something else. It's less useful,
Yeah.
arguably, but it's not lost, it's what it's supposed
That's
to
what
be.
people would trip up. People would trip up saying it's lost in heat energy in the light bulb, but it isn't. That energy is to be recorded.
But
it is
lost
in
heat
heat energy.
lost.
And it's internal energy that's lost in the battery. The batteries actually get hot when things go through them, especially when their cells put together. And this is where energy is lost.
And that is it, you just need to state, could be lost in batteries internally.
And
that'll be it.
That's the question.
Let's move on.
Let's move on to what's next. We're back, and on to resistance, the main part of this module.
EMFs and potential difference are important, are quite big things,
They are.
need practice, but they're not the main
No, they're more of an introduction. Because you did some stuff with GCSE resistance, but not very much.
So there was a physicist, George Ohm,
There was.
and he had a circuit, and he increased the number of cells in the circuit, hence increasing the potential difference of stuff in the circuit, and he noticed
That the current went up.
proportionally.
A nice straight line.
As long as the temperature is the same.
As long as the temperature is the same. So here's a
His own law.
he does his own law.
And it goes like this. The current of the components in a circuit go up proportionally to the potential difference in the circuit as long as external factors like temperature remain the same. Round of applause.
Yes.
So, stuff that follows Ohm's law is said to be ohmic, and stuff that doesn't is non-ohmic.
Sadly, Ohm's law's pants.
Pretty much everything is non-ohmic.
It's more or less only wires that do follow Ohm's law.
But how would you know if something does follow Ohm's law?
So as we're going to go through now, we have a lovely graph drawn by Wayne.
Potential difference.
Potential difference at the bottom, the y-axis is current, and for something that follows Ohm's law would be a lovely straight line, more or less like that.
So this one's said to be ohmic, spelt like this.
Yep.
But like we said, most things don't. This is pretty much only wires. Light bulbs, motors, all that sort of stuff, heaters, will follow a different pattern.
They will for different
That
patterns.
isn't a straight line.
They might start off the same,
They might.
but then as heat gets to them, it will go down. And LEDs do something quite strange.
Yes.
They do virtually nothing for ages, and then they
And
go
then they shoot up,
bonkers.
giving them huge resistances at these points.
It's true.
But both of these things are non-ohmic.
Yeah.
Ohmic spelled in the same way with just a non in front, just like that.
Yep. And with these, you might have to say what's ohmic and what's not ohmic. You look at the graph and you go,
So whatever's a straight line is ohmic. And these are
That's
the IV characteristics of components.
There's also a few equations of resistance.
Yep, let's swap places.
Alright.
I'll do it in green.
Okay.
Resistance, I'm going to put big R.
Yep, that's normally how resistance is denoted. Is equal to potential difference over current.
And that will give the units volts per ampere.
And the new unit, which is the Greek letter omega, which is ohm. Yeah,
It's drawn like this.
it is drawn like that. Oh, it's just like a little. I don't know what it's like really.
I don't even know. That is ohms. That should be a revision from GCSE. You should recognise that.
Yeah.
And that is the standard international unit. It's agreed. It's that. That's what it is.
It's a roller coaster. That's what it is.
If something is 5 ohms, it means you need a potential difference of 5 volts for the current in that circuit to be 1 ampere.
Yeah. So we should go through a few questions.
Questions? Alright, I'll read the question. You can write it down.
Okay, so I'll write it below the graph, I think. That's a green pen. Here's the black pen.
Okay, we're going to do number 2.
Alright, so number 2. Let's go.
This is page 99. Resistors manufactured on a commercial scale are available only in certain values. These are known as preferred values. The E12 set contains 12 values which include 10, 15, 22, 33, 47 and 68 for every power of 10. The question is horrific, but the actual questions themselves are not.
Okay.
So, A, calculate the current in a 33 kilo ohm. Okay, 33 kilo ohms resistor connected across a 5 volt supply.
Great. That's the information we'll be given. So let's use our equation.
Yep, we're just going to be using this equation. It's nothing special. We're
I
going
think
to
the
rearrange.
first step is to maybe put this into the same units as the rest.
Yes, this is kilo ohms. We want it as ohms.
Kilo is the same as
Times 10 to the 3.
Yep.
So 3.3 times 10 to the 3.
Is it 3.3?
Oh.
It's 33, which is 33,000. It's fine. I can do that sort of maths in my head.
I don't know why I needed a calculator.
I'm not sure. You're just showing off your very flash piece of kit.
Yeah, it was quite a lot.
Yeah. How much was it again, Wayne?
It's about 50 quid.
Oh goodness.
Ridiculous.
That.
33,000. And then we want to rearrange this equation to make I, current, the subject.
So just swap those two really.
Yep, it's going to be 5 divided by 33,000. This I do need the calculator for. You ready?
Yeah.
It's 1.51 times 10 to the minus 4
All right.
amps.
Which would be the same as 0.151 milliamps.
Yes, so there's a part B.
I think.
Part B is calculate the potential difference across a 2.2 mega ohm
Yeah.
resistor carrying a current of 6.2 microamps. Remembering micro is the weird U-shaped.
I guess you want to find out.
You want to find out V.
E.
So, again, we'll get these all in their normal. Mega is times 10 to the 6.
It is.
So it's going to be 2,
2.2.
2, and then 5 noughts.
Or we could just write times 10 to the 6.
Good. This is going to be 6.2 times 10 to the minus 6, this one.
Yep.
So I'll type that in there. 2.2 times 10 to the 6 times 6.2 times 10 to the minus 6.
12.4.
13.64.
Damn.
Trying to show off your mad maths.
No.
Last question is part C.
Part C. I'm
Are
not
you
sure
ready?
I'm going to put it. I'm going to put it up here.
Okay, this time is calculate the resistance, so we've done all three now, of a resistor which carries a current of 13 milliamps
Yeah.
when connected across a 9-volt battery.
It's the final one.
We are actually using this equation as it is, and it's going to be 9 over 13 times 10 to the minus 3. 9 divided by 30, oh bloody hell, 9 divided by 13 times 10 to
It's
the
quite
minus
a lot.
692.3
Ohms.
ohms. And now let's get on to resistance of the components themselves.
Alright. Let's crack on.
Back.
We are back into resistance and components on a circuit.
So, we're going to go through the examples of filament lamp and LEDs.
We are going to compare them. And should we do the graphs, both of them?
Yep, the IV characteristics.
Alright. While we're interested in that, I'll talk a little bit about the bulb one.
What's this one?
Bulbs get quite hot. You might have noticed if you grab one when it's been on for quite a long time. And that's because high current things get hot. That's sort of how they work.
Yes, increasing current increases temperature.
Yeah. And this also means that they're non-ohmic.
Yep, because it's not a straight line, that's how you can tell, but that is what it looks like. And that is a familiar IV characteristic you'll have to be able to draw and replicate in the exam if asked.
It is.
And it's likely.
And do you remember the other one?
Yep, LED.
And you might have to compare them to a LED and sort of benefits of an LED or slow points of a filament light bulb. One of them is the temperature thing. They get very hot. Very, very hot. In fact, 80% of their energy is heat.
Yes,
Not
and they're
light.
not very efficient
They're
at
not
all
very
in terms
efficient.
of light. They're better at giving out heat.
Yeah, LEDs, however, are quite good.
Yes.
Turn on straight away because they need a very low working current.
They'd be very cheap to run because of the low potential difference. So if you give the same amount of energy to this as you do to this, you'll be able to spread it out over much longer to get it to
Yeah.
work. You've got them in clusters and they're much brighter and better than normal lights.
Yeah, and also very robust, quite hard to break LEDs unless you put far too much energy into them.
Yes, and that is a lot of benefits over LEDs. They're quite expensive to make because they're tiny. Like an LED on its own
It's very
isn't very big at all.
No.
You need lots of them, and because they're diodes, they only let stuff flow one way.
This kind of makes it a bit awkward for big circuitry, like tellies. That's why they cost quite a lot because, well,
Everyone has to be put in the right way, so that you can imagine how much time that takes. Obviously, machines do it, but it takes a lot of
it
time
does
and
take a lot of
effort.
time. And if something does go wrong,
You got to find the diode responsible, which is madness.
they're
and
just very little.
get rid of it. That's why it's expensive.
Yeah. Is that all for this bit?
I think that's all.
So we've got a
just
question,
remember
really?
these two shapes, and we have a question.
Alright, so I'll grab the book.
Okay.
Okay, cool. I don't know what I'm worrying about.
I don't know what you're about.
So we're doing question 2.
We'll do question 2.
Okay. A diode usually has very low resistance when connected in a circuit in a direction that passes the circuit. Go ignore them. To limit the current in the circuit, the usual procedure is to add a safety resistor in series with the diode. When a 220 ohm resistor is connected in series with an LED to a 4.5 volt supply. Cool. The current in the circuit is 10 milliamps.
Okay.
Calculate the potential difference across the resistor and hence the resistance of the LED. That's the whole question.
Across here.
here's your red pen.
Red pen. Are you going to talk me through what I'm doing?
Yeah.
Okay.
Yeah, right.
Get on with it then.
Okay, like before, we have our equations we've been using for most of this unit. This is voltage over current, or potential difference. Rearrange this to give voltage. We are going to start off by finding the voltage going across here. It's 220 times 10 times 10 to the minus 3, which is just 2.2.
Is it just 2.2?
I think so, is it?
Yeah.
Yeah, it is. It's 2.2 volts. And then it says, and hence finds the resistance of the diode.
Okay.
So that will be the difference in the two. Because if the internet goes one direction, that's very low resistance, so the only resistant thing is going to be here.
It's gone from 4.5 volts to 2.2 volts.
It has, means a difference of 2.3 volts. So we just plug that one in instead. So we have 2.3 divided by 10 milliamps, 10 times 10 to the minus 3, and that will give us 230.
Yes,
and that's the resistance of our light emitting diode. And that's the question. It's quite simple, really. You just have to think about the question a bit.
The only difficult part would be to know about the volts across this, the potential difference across this.
Yeah.
Is going to be that minus that, because that's how much all of this gets to here, only that much gets to here.
Yeah.
How much is lost, and it's just making that connection.
I think that's pretty much it for that bit.
Yes, now we go on to resistivity, but we've made a part 2 video.
Yeah, because the video is
of this
quite
topic.
long otherwise.
Yes.
So yeah, see you at part 2, wherever we link to that.
Yes.
Yes.